All right, so we have chapter 26, image formation by mirrors and lenses. So we're going to continue exploring the optics branch of physics. So we are looking at, kind of continuing from chapter 25, where we learn about the, light changing direction, changing speed when it goes from one medium to another. We learn about the, ray model of light. So we're kind of going to continue with that in this chapter. So remember, so we have this two models, right? So we have a wave model, which allows us to look at all the wave properties of light. So let's say here's a wave moving as a light moving as a wave, and it has a a wavelength between two crests, and there's a frequency, and then frequency times wavelength is the velocity of the light, and if it's moving in air, then it's a speed of light. Same in air and vacuum, right? So those things are useful when you're considering the uh, how the light behaves as a wave. But we learned in the in the previous chapter, when you're using the Snell's law, especially, right, it's more useful to use the ray model. So the ray model was kind of like simplified way of representing light, just as an arrow like that. And this diagram, right, using this model, right, using this ray diagram, we could easily see how, let's say, the light as it enters a new medium, and there's some kind of theta 1, right, with respect to the normal, then it will go in terms of like theta 2 from medium 1 to medium 2. It will change direction, it will change the speed and all those things. So that's why we're going to continue using the ray model of light, because when you consider mirrors and lenses, it's much more useful to use the ray model rather than wave model. So that's what we're going to do. So again, we're going to use ray diagrams, right? So it's to study the mirrors and lenses, and we always going to assume it's a specular reflection. That means whenever the light hits the surface is very smooth, so there is no diffusion. So that's why what we're going to do here is, instead of, let's say, using all the light rays, we can just maybe use one or two or three sample ones, and then we can assume more or less the rest of them are kind of similar in terms of everything else. All right, so this chapter basically going to be using a lot of geometry, so make sure that you guys are more or less familiar with geometric, let's say, angles and things like that, because the idea here is that as simple as they are, right, so there's a little of geometry involved, and we will be using position, or to determine the position of the image, let's say, or the height of the image, using pretty much this array diagrams and using a little of geometry. All right, so let's look at then what our first, let's say, type of experiment we can have. And we're going to actually start with mirrors. Okay, so the mirrors come with kind of like in two types: a flat mirror or a curved mirrors. So let's look at the simplest one, which is the flat mirror. And that's the one that most of you probably using, right? And if you have a bathroom mirror, or in your closet, right, something like that. If there are mirrors, usually they're flat, plain mirrors. So what we're going to do here is we're going to try to find the mathematical equations, or the conceptual understanding of the image formed by the plane mirror. Now, what we have here, you can see in this picture diagram, right? So there are three things. So basically, two important things are the object and the image that is formed for this observer over here. So we have object here. So we have the image here, and we have the observer. Okay. And observer usually, let's say, you can think like when we find the image, we're finding the image for an observer who would see that image. All right, so usually we're going to say we're going to use O for the object and I for the image. Okay, so we're going to say that if you put an object in front of the mirror, then the image created of that object for the observer will be represented as just I. And also we're going to then use P to represent object distance from the mirror, and Q to represent image distance from the mirror. Okay, that means you need to know not only the, let's say, position of the image, you also need to know the position of the object, how far away the object is from the mirror. Okay, so in a way, we don't really care where the observer is. So the observer here, you can say that we use the observer to, to understand where the image will be. So anyways, the O is the position of the object, P is the distance of that object from the mirror, I is the position of the image, Q is the, distance, from the image to the mirror. All right. So one thing we have here, as you can see, right, the images are located by extending diverging rays back to the point at which they intersect. Because one of the things we have here is, if you kind of look at those rays, the object here, and there are generally, like let's say all of our objects, we're going to assume that, generate light, okay, or there are light sources. And there are two types of objects. We don't really need to know, let's say, exactly what type of object it is, but generally in physics, we consider two types of objects. Objects that make their own light and generate their own light, like the lamp or the, let's say, the sun, right? So they, if you consider them as a light source, they generate their own light, and that light kind of radiates, in every direction. So for example, if you have the sun, right? So the sun radiates light in every direction. So those are the rays from the sun. And if you're observer, if you're here, right? All right, so let's say, I don't know, so let's say these are your eyes, right? You're looking from here, you will see maybe this one, but you're not gonna see the other one, right? But still, one of the things we have here is we assume that light source generates light in every direction. So if you look at it directly, you will see it. But there are also, sources where, that don't generate their own light, but they can reflect light, right? So everything that you see around you right now are, this type of objects. They reflect the light. So the light bulb generates light and radiates, and that means, and that light hits a surface like a table in front of you or computer, right? And that light then reflects off of that object and reaches your eye, so then you can see that object. If you turn off the light and there's completely dark, you're not going to see that object, right? Because there is no light reflecting off of it. So that's kind of like the idea. So what we have here is then, for us, it doesn't matter what type of object it is, because even if it's a reflecting object, right? So, you should be able to assume that it kind of like generate light like this. Okay. All right. So then what we have here is, let's say the important thing for us is, let's say, okay, so take the object, put it somewhere in front of the mirror, some distance P in front of the mirror, let's say, right? And, let it basically radiate light, okay? And what we want to see is that, can we find the image of the object, not by directly looking at the object, by looking at the mirror. Okay, so you can see, right, we're looking at the mirror, but because the object is in front of the mirror and the light that object generates can move and hit the mirror and reflect back off of a mirror toward you, you can actually see the image as well. So that's why one thing I have here is this light, or sorry, the object, right, or the light source generate light in every direction. And then according to the, the law of reflection, right, that light will, kind of like radiate like this. Well, not this one, it kind of goes like this. But obviously, if you are here looking at the, mirror like that, in that direction, those ones, not, they're never going to reach your eye, so you're not going to see that. But because of the way that this object radiates and, the light, at some, some rays will definitely reach your eye. So this guy here, you can see, right, hits the surface, reflects. That's not going to technically reach your eye. This one hits the surface, reflects. That one you're going to see. The next one, you're not going to see. But let's say, assume that there's maybe a detector that can detect, if not your eye, some kind of detector. Then where is the image? Well, the image will be, because one of the things you can see here is as the light, so incident lights, they hit the surface, right? Hit the surface of the mirror, they move such a way that they are moving away from each other. See this direction of the rays? they diverge away. So that's why those are diverging, means that, you know, they basically moving away from each other. So the light that is reflected from the plane mirror diverges away. That means they will never intersect at any time in front of the mirror. But what we can do here, what we can see is that if we take those 3 reflected rays and we, you know, trace them back into the mirror, then we can see they intersect right at that point. As they intersect at that point, the point where 2 or more rays, real rays or extended like this, right, intersect, that's the position of your image. So that's your image, okay? That means what we have here is images are located either at the point from which rays of light actually diverge, or at the point from which they appear to diverge. Because in a way, what you can see is that as you move back, right, as you extend that reflected light and reach this position, you know, I, right, it seems like all those reflected rays started from that position and then kind of diverged away. All right, so in reality, this is where they diverge away from, but they appear to be diverging away from that as well, okay? And that is where the image of this object will appear inside the mirror. Then one thing we can do here, we can then also measure the position of that image. And again, you know, we can represent that with a Q. So image distance Q is the distance from the image to the mirror or lens. All right, now, okay, so we see that, you know, let's say image, then the images come in 2 types, a real image or a virtual image. So the question here is, what type of image was that? All right, so it's easy, it will be easy for us if we actually understand the definition, right? The formal physics definition of a real image and a virtual image. And here's for the real image. Real image is formed when light rays pass through and diverge from the image point. Okay, but the idea here is that that image point should be where actual light rays going through that point. All right, so if actual light rays go through that point, then you have a real image. So if you come back, you can see, right, this is where the image is. Do we have actual light rays intersecting and diverging from that point? Well, no, right? Because actual light rays never go behind the mirror, right? They never go to that point. They diverge away from here, but we can extend them back. So that means that's the real, you know, that's not a real image, because no actual light rays go through that, you know, position I. All right, so the real images can be displayed on the screen. That means, you know, one of the things we can see here is if the, you know, if the device, right, gives you a real image, you can put a screen right there and see the image, okay? That means, for example, if I kind of go back here, see, let's say this is the mirror. And one thing I can do here is, for example, if I put a screen right there, there will be no image on that, because this is a virtual image. This is it's not a image where the actual light rays, you know, go through that point. So let's say even if you have some kind of thin mirror, right? So if you look through the mirror, you will see the image, and image will seem like, you know, maybe like a meter behind the mirror. But if you go and put the screen meter behind the mirror, there's nothing there. On the screen, there is nothing there. Only when you look through the mirror, you will see that image, but you will not see the image on some kind of screen. But the real image can be displayed on the screen. Okay. So again, so virtual image is formed when the light rays do not pass through the image point, but only appear to diverge from that point. And you could see that's the case for the, you know, plane mirror. So virtual images cannot be displayed on the screen, and that the image of an object seen in a flat mirror is always virtual. All right. So flat mirrors always gives you virtual. Does it mean all the mirrors gives you always virtual? No. Flat mirrors always gives you virtual, but there are some curved mirrors that can give you actually a real image. And we're going to look at that in a little bit. All right, so now let's say there is an object with some height. So let's say, think of it yourself, right? You're standing in front of the mirror. That means you have your height, and then height is given with h, okay? So then P is the position of consideration. That means we're considering, let's say, the tip of the arrow, right? And what we want to know here is how we can use ray diagram to find and generate, or a image, in the mirror, either in behind the mirror or in front of the mirror, depending. And again, for the flat mirrors, is always going to be virtual behind the mirror image. But let's say in this case, we want to know how we can use geometry, right, or those ray diagrams to find the image. So what we do here is, let's say, take that point P, which is here's our point of interest, and draw at least 2 rays. Because remember, the idea here is that image is where 2 or more rays intersect. So with 1 ray, this will never work. So let's say what I do here is, all right, so there's a mirror. Let's say the light is incident. You can see, right, it goes and hits the mirror. And this is perpendicular to the surface. Now, what we do here is we place the object on the axis. So this axis you can see, right? So this axis then will tell you if the image is, upright or inverted. So in this case, you can see both of them upright. So like, let's say for now, an object, right, is upright. It has height h. So then this first line has to be, sometimes I call it P ray, because this is parallel to the axis. So this axis that I have, right? So then the P ray is parallel. Okay, that means 1 ray starts at point P, travels to, this position Q, let's say. And that position Q here is parallel to the point P. Okay, so now if the light, we learned in the previous chapter, right? If light is incident, let's say, to the surface with 0 degrees, right? Then it's going to bounce back with 0 degrees. That means it's going to reflect back with 0 degrees. That means, remember, this is a mirror, and mirrors do not allow transmission of light. There is no propagation, no refraction. So as the light hits the surface at point Q, it's then going to be reflecting back, on itself like that. All right. Then what I do here is I take the reflected light and trace it back into the backside of the mirror. All right. So, but there, let's say we didn't have this, other ray yet. So that's not going to give us much. That means then what we do here is we use another one. Okay. So another ray. So let's call this point R, right? So generally this is known as a vertex, right, at the center. So the second, ray then gonna go from P to R, right? So, and then it's gonna hits the R, then it's gonna reflect back. So as it reflects back, it still obeys, law of reflection. Okay. All right. So what do? We take it, we then trace it back, the reflected light, right? We take the reflected light, trace it back behind the mirror, and then you can see, right, at that point, this, PQ line and, let's say this R, the reflected PR line, they intersect. That means at that position is the P prime, and that position is the image, the tip of the image of the object. And then you can kind of like draw this arrow like that and say, all right, so from the axis, right, to that point P prime, that's my image. Okay. Now, you can see, right, the triangles PQR and P prime QR are congruent, all right? The image formed by an object placed in front of the flat mirror is as far behind the mirror as the object is in front of the mirror. That's also another thing that is very, unique to the flat mirrors. That means P, which is the, distance of the object relative to the mirror, is equal to the Q, which is distance of the image relative to the mirror. All right. And there's a reason we actually use absolute volume, because what I have is that so the image formed by an object placed in front of the flat mirror is as far behind the mirror as the object in front of the mirror. That means this is what we have is true always for the flat mirrors. That means, see, the key here is distance, all right? Because if you're considering, in this case, if you're considering for the mirrors, okay, for the mirrors, this Q here is then going to be negative if it is behind the mirror. What is behind the mirror? The image, obviously, if the image is behind the mirror. So that means the Q, which is its position, is negative. So that means, let's say for, let's say P here is 5 centimeters in front, then Q will be 5 centimeters, but behind. So technically there's a negative. So that's why we use absolute value to, you know, indicate that their distance is the same. But, you know, one is going to be positive, the other one is going to be then negative. Also, one thing we can see here is the H, which is the height of the object, and H prime, which is the height of the image, also equal to one another, because you don't stand in front of the flat mirror and you see yourself like half the size, right? Always the size matches. And that is true for the, you know, let's say the flat mirrors. Now, one thing we can do here is to use the ratio of height, image height over object height, H prime over H, to find what we call lateral magnification. The magnification basically will tell us if the object and image have the same size. Because, for example, if I calculate this and let's say I get 1, H prime over H, I get 1, that means they are of the same height. Well, also I can get this, right? So technically what I get here is +1. If I get +1, let's say the image here is 5 centimeter, object here is 5 centimeter height, right? So I'm gonna get +1. So the +1 indicates that image has the same orientation as the object. Because, for example, if I find the magnification of -1, means that image is inverted compared to the object. So that's why there's a, you know, plus minus in front of the quantity for the magnification also tells you the, you know, the orientation. All right. So this is the general magnification for any type of mirror. That means any type of mirror, and later on we're going to even see any type of lens will be, you know, using this equation for the magnification. So in a way, again, magnification tells you if the image has a different size, a different orientation. Okay. So it's also valid for the images formed by the lenses. Magnification does not always mean bigger. The size can either increase or decrease and can be less than or greater than 1. All right. So because, for example, if you get, you know, m equals 2, that means that, you know, see, this means H prime over H, right? How can it be 2? It can be 2 if the image is double the, the object size. So H over H, you get 2. That means image is twice the size. All right. So then you can get, let's say, 2. So in any case, what we have here is the lateral magnification of a flat mirror is always 1. Okay. That means if the mirror is flat, you're never going to get anything more than 1. If m is not equals to 1, let's say +1, right? That means you're not dealing with the flat mirror. All right, so let's look at this example here. So you are 1.62 meter tall and want to be able to see your full image in a vertical plane mirror. What is the minimum height of the mirror that will meet your needs? How far above the floor should the bottom of the mirror be placed, assuming that your top of your head is 14 centimeters above your eye level? Okay, and we're going to use array diagrams to basically do that. And here's the image of that, sort of like, let's say. So the mirror doesn't have to be all, you know, the entire, you know, size of, basically doesn't have to be 1.62 meter tall, because the array diagram tells you that, let's say these are your eyes, so you can see top of your head from on the mirror, because it goes like this, hits the surface and comes back. And that means the distance from your eye level to the top of the mirror can be half of the distance between your eyes and your head, right? Because it doesn't go like straight and come back, right? It has to go halfway and then strike it and come back. All right. That means what we get here, what we get here is that, you know, in the array diagram, right? So let's say you can see, right? Distance here, let's say this distance should be, since this is 14 centimeters, so this should be half of that. So it should be 7 centimeters. Okay. And then what we have here is, well, that means from here to the ground, right, is then 162 minus 14, right? So that means, let me see. Okay, so let's say for here, you know, if you take this one, right? So this is again, your feet hits the mirror and then come back. That means you need to have minimum height over there so that it basically hits the surface of the mirror and reflects back toward you. Okay, so the question is, what is the minimum height of the mirror, right? So the mirror must be generally half your height. Okay, so that means the mirror has to be about 81 centimeters. Okay, and then what you do here is, let's say, how high above the ground should it be from the ground? Then it should be, you know, let's say you take in 155, right? So which is 1.62 minus 7. So you take that in terms of that's 7 over there, right? So minus 81 centimeters. So you get 74 centimeters, right? That means the mirror here should be 74 centimeters, let's say, in front, above the ground, okay? So that if it is 74 centimeters above the ground, then you should be able to, standing in front of it and see your, let's say, your feet, right? And then it should be, here 7 centimeters above your eye level. So then you see the top of your head. All right. Now let's look at images formed by spherical mirrors. That means these are curved mirrors. All right. So, and one of the things we have here is you can think of, like, let's say you take some kind of, a spherical mirror, right? And you can technically cut it in 2 different shapes. So you can cut it like this. So kind of like take this side, right, and cut it like that, or cut it like this, the second side. So that means you can take this side or you can take the other side, right? So each one, give you completely different, actually, image, formation. So then what we're going to do here is we're going to then say that the spherical mirrors have a shape of a segment of a sphere, and the mirror focuses incoming parallel rays to a point. So let's say then this particular shape, right, this particular part of the, sphere, if we use as a mirror, this is known as a concave mirror. Okay, so concave mirror. Sometimes it's also known as a diverging mirror. So diverging mirror, but concave is more commonly used name for that. All right, so what we have here is basically, you can see, right, so we have this axis, let's call it principal axis. So the principal axis basically goes through the, so let's say if this was your sphere, right? So this is the, okay, so let me do, this is your then principal axis. So remember, it's a sphere, that means it has a center, and then there's a radius distance from the center of the sphere, right? Now what we're doing here is we just then carving this part, right, and just using this one. But still what I have here is from the center to the, to the, let's say, center of your mirror, right? Then it's a distance radius, 1 radius distance, okay? And that means, technically to any, from this point C, right, to any part of your mirror is also, distance R, right? So like that. All right, that means we kind of ignore this other parts of the, the sphere. Then we only have, let's say, this segment. So this is known as a concave mirror. All right. Okay, so with the concave mirror, then we can start doing measurements in terms of if there's a light incident to that mirror, then that light, so technically can be redirected, reflected from this mirror, and we can have an image, like just like the flat mirror. All right, so the mirror has a radius of curvature R. The center of the curvature is point C. Then what we have here is which is going to be important for the curved mirrors. This is known as a vertex, right? Point V is the center of spherical segment. Okay. And what we have here is a line drawn from C to V is called the principal axis of the mirror. All right, so let's then consider an object, O, some distance, remember, so we can then represent as P from the mirror, okay? And it generates basically a light which kind of radiates in every direction. So what you can see from here is that, let's say using a couple of rays, so this guy goes, let me use a different color so you can be able to follow what I'm doing. So let's say this one here goes, hits the surface, then follows the law of reflection, so reflects back. Here's another one, goes like this, hits the surface, follows the law of reflection, reflects back. And I can do the 4 other ones. So let's say this one can go there, hits the surface, follow the law of reflection, and it's gonna then reflect back like this, more or less. And if you follow every line that is generated from that object, hits the mirror and reflects back, they all on average will be going through that point. Remember, the image is formed when lights, either real lights or the extended lights, right, go through some point. And you can see, right, if I take this as my point, those lights appear to be diverging from that, right? That means this is now my image. And then I can say then this is Q, which is the distance of that image from the mirror. Okay. That means we can use those 2 diverging points to show, like, from the basically diverging lines, right, or rays from the object. We can see that they are intersecting at that position I. Okay. And as they intersect at position I, then that's an image. Now, what type of image? Is it real or is it virtual? Well, remember, the real one is when actual rays, right, go through that. So real means that real rays, right, go through that. For the virtual means that sort of like extended, that means you extend them back, right? Those are the ones that going through, right? Then you get virtual. But here, those are actual rays that go through that point. That means this is a real image. So you can see, right, a mirror can give you a real image. That means here a concave mirror can give you a real image. All right. So now let's consider, instead of a point, let's consider actually some kind of object with height. All right. And what we're going to do here is, so I'm kind of, going to give you a step-by-step breakdown. So let's say this is our print. Let me try to straight line. This is our principal axis. Let's say this is our mirror, like a curved mirror like that. All right. So what I'm going to do here is I'm going to place an object. All right. So here's my object. Okay. And this is its height h. Okay. Now, there are technically several cases of the, let's say, the image formation. And more or less, we can, talk about that a little bit later on. But for example, where the image, what type of image will we see depends on the position. Remember, this is going to be the P, right? Position of the object relative to the image, mirror. So, but also its position relative to the C, which is the center of the curvature, also plays a big role. Okay. Now, what I have here is this then. I can use, remember, at least 2 rays. You need to at least 2 rays, but generally we can use 3 because you use 2 to you can use 2, see where they intersect, and then use the third one to, more or less verify. All right. So here's the rays that you can use. Okay. So one of them can go, let's say, through this point C. So let's say if it goes through this point C, it's going to hit the surface, such that it's exactly, going, let's say, through the normal of that surface. So then it's going to reflect back on itself like this. okay? So that means it goes, hits, and reflects back. Then you can use another one that hits the vertex. It's gonna go, hit the vertex, and then reflect back. All right, goes like this. That means those two right now, enough for us to see this two lines intersect, okay? And if I do that, I can see that going from the principal axis to that where they intersect, right? So this point I, right? So that means I have to go back, go down like this, and that's where basically my image is. Is it a real image? Yes, because actual rays going to that point. Is this upright image, same orientation? No, you can see it's inverted. And you can see also that H prime being the height, it's also smaller, okay? That means what we get here is an image that is real, but also inverted and smaller than actual object, okay? That means you can have an object, you know, in front of the mirror, some finite size distance in front of the mirror, and what we get here is we get then object in front of the mirror with the finite size, so you get an image that is smaller than that. Doesn't mean that all the images generated by the concave mirror are smaller. Some can be bigger, some can be same size, and we will see, let's say, some what cases then we can use to kind of go with that. All right. So by convention, these distances are measured from the point V. Remember, like let's say distance of the object, distance of the image, point C, and all of those things. So one ray passes to the center of the curvature C of the mirror, hitting the mirror and reflecting back on itself. So kind of review that. The second strikes the mirror at the center point, obeying the law of reflection. And mathematically, those things are related to one another with this equation. And this is known as a mirror equation, which means 1 divided by the distance of the object plus 1 over distance of the image equals 2 over the radius r, okay? And those, those quantities are basically the important thing, right? CP, Q, and R. So that means, where is the object, where is the image, and where is the center of the curvature of the mirror. Okay, so this mirror equation is the one version, the first version you can think of like is of this mirror equation. We're gonna see another one in a little bit. All right. So what we have here is the image of the tip of the arrow is at the point at which these two rays intersect. Yes. All right. So now here is kind of like using a little of geometry where you can kind of like break it down into two, let's say, triangles, right? There's one triangle here with alpha, which ends up being the same, alpha on the other side. And then there's a theta over here, right, with the second triangle. But, you don't have to worry about it so much in terms of derivation. The idea here is that magnification equation that we had HI over H can also be written if we kind of, use those triangles. And we can see that if you kind of use those tangent of those angles, right, and we're going to come up with the equation where we end up magnification to be also equals to the negative Q over P. That means magnification is also a ratio of the image distance over the object distance, but then there's a negative over there. Because in this case, you can see, right, the height is basically, negative because the image is upside down. But, this is going to be general equation where the magnification now has two equations, one in terms of the ratio of the heights, the other one in terms of the negative of the ratio of the distances. So it's going to be a very useful equation that we will see later on. All right, so here's one case that we can consider for the concave mirror. Where is the image and what type of image will we see if we take the object to be really far away? Okay, so let's say you can remember that equation, 1 over P plus 1 over Q equals 2 over R. Now, if I assume that image formed of an object that is really far away, so remember what is, like, let's say the really far away means. It means that, you take P to be infinitely far away. That means it's infinity. So if I come back here and I replace P with infinity, well, 1 over infinity is 0. That means I get 0. That means what I have here is then 1 over q equals 2 over r, right? If 1 over q equals 2 over r, means q equals to then r over 2, which means the image distance is r over 2, half the radius. And we can see that from this diagram. See, if the object is really far away, the light is parallel to one another, right? Those rays are going to be parallel to one another. So when they strike the mirror, they're going to diverge, so, converge actually to this point F, which happened to be exactly, so this F is the focal point. So its position here is exactly half of the radius. Okay, so that means this point F is known as the focal point. Okay, so that's the focal point. And the lowercase f just represents how far away that focal point is from the mirror. And it is known as a focal length. Okay, that means what we have here is the image formed if the object is infinitely far away, exactly at the position which is half of the radius. Okay, so we call that focal point, or we call it the focal length. Okay, so that's kind of like what we have. That means that for the object really far away, you can always assume that rays are parallel to one another, and we get that. So the point at which the parallel rays intersect after reflecting from the mirror is called the focal point of the mirror. And the focal point is a distance f from the mirror called the focal length. That means you can always use that, focal length also in some of this calculation. Now we have the r, which is the radius. And then remember, this is distance of this point C, right? How far away the point C is from the mirror, which is the radius distance. Now we have a focal point, and the distance of the focal point to the mirror here is lowercase f, which is focal length. Okay, that means technically focal length is then half of the radius, because focal point is half of the point C. And what I can do here is remember that r over 2, right? So is the focal length, and our original mirror equation was 1 over p plus 1 over q equals 2 over r. See, if I take the square root of or inverse of those two, that means 1 over f is equals to 2 over r. Then in this equation, this can be then replaced and written in terms of just 1 over f. And generally, this is more preferred version of that. So 1 over distance of the object plus 1 over distance of the image equals to the 1 over the focal length. All right. Next, we have convex mirrors. So the convex mirrors are called diverging mirrors because the light reflects from the other convex side. So remember, that's the other side of the the sphere, right? If you're considering. That means when the light is, let's say, coming from the object, it interacts with this part of the sphere. Okay, and the rays from one point of the on the object diverge from the reflection as though they were coming from some point behind the mirror. Now, one of the things we have about this convex mirrors, they're actually very simple to work with, because you're always going to get exactly same thing. So the image that's going to be generated, right? So for example, this is the principal axis. This is your convex mirror. So let's say if I have an object there, it doesn't matter where the object is. So let's say it has a distance p from the mirror. So for example, then what I have here is, remember now, because of the shape, point C and F are on this side. So one ray that technically has to go through point C, it goes like this. Oh, let me try again. See, it goes like this, but see point C on the other side. So it's actually, so what we do, we extend it so it goes to that point C. And then the other one, let's say, has to go to the point F. So let's say it goes parallel, and then it reflects like this. So then it has to go to this point F, right? And what we can see here is, it's not ideal. So this one, I didn't really do that well. So this one gonna go like that. Okay, in any case, so they intersect somewhere over there. Okay, and then you can see, right, that's basically where my image is, behind the mirror, and it's same in orientation as the object, and it's much smaller. And that's kind of what we get with this type of, um, mirror. With the convex mirror, you always get a virtual and smaller image. Okay. So you get always a virtual and smaller image, because it doesn't matter where the object is relative to the mirror, this is going to be always true. Okay, so you can see over here. So you have the object, and you use those two principal rays, right? So one has to go to the C, but obviously it's going to hit the mirror and bounce back because C is another side. We extend it, trace it back, and then the other one has to go to the focal point, but focal point is again on the other side. So but it's if reflects, so then you trace it back, because of all the lights, right, when they interact with this convex mirror, they're always going to diverge away. That means they're never going to converge somewhere in front of the mirror. The only way those light will converge if you trace them back, right, extend them back, behind the mirror and find a virtual image. All right. So the sign convention is very important for the mirrors, because if you're using flat mirror, convex mirror, or concave mirror, you need to understand that you're dealing with things like, so you have P, Q, R, and I guess F. So those are the quantities that we have. And plus, I guess, H and H prime. So those are your variables. Okay. And those variables can be positive or negative depending on, let's say, what type of mirror you're using. But it's generally, there's a standard what we use. So in terms of, it's one way of kind of like understanding where you put one positive, where you put one negative. And it's all about, let's say, I've been kind of trying to, give you the hint about those, right? So in front of the mirror, back of the mirror, and things like that. So this is kind of what you can see. So the region in which the light rays move is called the front side of the mirror. So you can see, right, front of the mirror. This is also known as a real side of the mirror, because only in front of the mirror, the light will actually be able to converge. Remember, there's absolutely no real light going to the back of the mirror, right? Because it's a mirror, it reflects everything, everything back. That means the front is the, real side. Okay. Now, P and Q are positive if the object is in front of the mirror and image is in front of the mirror. That means both P and Q are positive. Okay. But if the P and Q are in the back of the mirror, because sometimes you can have two mirrors or something like that. So, but if P and Q in the back of the mirror, you can have them negative. Mostly we're looking at the Q image to be back of the mirror, and Q is always negative when it's in back of the mirror. Okay, remember, there's absolutely no light over there, right? No actual light. So that's kind of what we have. So sign convention is important to understand, because we always have positive or negative for the image position, depending if it's in front or in the back. Okay, so technically thing like this. So if image, right, so if image is real, then Q here is positive. If it's virtual, then Q here is negative. Also, if it's real, it's always going to be, if it's virtual, it's always going to be upright, so H prime is positive. Okay. Also, the same thing we can do for the focal, length, right? Focal point and radius and things like that. Because remember, the focal point and radius, or point C, also in front of the mirror or back of the mirror. So you kind of have to look at all those as well. So for example, this is kind of like the complete one, right? So you have, P, you have then Q, you have then H prime, and then you have the focal length and the radius, and then magnification. And this table will tell you where they are positive, where they are negative, right? So you should be able to follow those. So you can see, right, object is positive in front of the mirror. Image is positive if it's in front of the mirror. Height is positive if image is upright. Focal length and radius positive for a concave mirror. Because see, here's a concave mirror. See the focal length and C, right? Both in front of the mirror, so both positive. If you have a convex mirror, then both focal length and C are in the back, so and F and R are both negative. So you can see. But how about the flat mirror? Well, flat mirror, so think like this. So if you have this guy over here, which has now radius R. See, if I start flattening this, so if I flatten this, see the R changes. How about a little more? R increases. How about a little more? R increases. How about a little more? R increases even more. How about if I have something like this? Well, this becomes, that means the curvature. So it's the mirror is so flat that if you consider a curvature, you have to extend all the way to infinity to see some kind of curvature. That means for the flat mirror, right? For the flat mirror, radius for the flat mirror, right, is infinitely large. Basically, it equals infinity. Okay. Or how about the focal length? Well, if this is infinity, right? Remember, this is R over 2. That means this guy is also infinitely large. Okay. That means that's why if I'm using this equation, 1 over P plus 1 over Q equals, let's say 1 over F. Well, if it's 1 over infinity, then that becomes 1 over infinity is 0. That means 0 is equals to 1 over P plus 1 over Q, which gives you P equals Q, right? Well, absolute value like that because, you move it to the other side. All right. Okay, so to draw the ray diagrams, you need to know the position of the object, the positions of the focal point and the center of the curvature. So we're going to use 3 rays to draw those, and they're always going to start from the object, some position of the object, and the intersection of any 2 of the rays at the point locate the image. Okay, and let's say the 3rd ray generally then is served to kind of verify that. Okay, so we're going to use that to verify the position of the image. Okay, and to do that, again, we're going to use 3 rays, and we'll talk about that in the next few slides.